I will demonstrate to you another data mining tool, but this one is from commercial world, an industrial tool. Tool is called Ibm Spss Modeler, arguably one of the most popular data mining tool, commercially viable in the marketplace. So going back to our Gartner's Magic Quadrant for Advanced Analytics Platform, as you can see, Ibm Spss Modeler is in the leaders quadrant, very closely related to SAS Enterprise Miner. Those two tools are leading the market by far as the market share and capabilities are concerned. So let's go right into the demonstration of Ibm Spss Modeler. This is the icon that it generates once you download and install it. By the way, this is a commercial tool. To be able to have a copy of it, you probably need to purchase one from IBM. If you are in an academic institution, most academic institutions can actually apply for a software grant. That means you can actually get it for free if you're only going to use it for educational purposes. When you launch the software, it shows up somewhat similar to how KNIME looked like. In this case, the icons, the tasks are at the bottom of the graphical user interface. We have a workflow pane here where we're going to drag and drop this graphical icons to build a process for data mining to generate results. On the right-hand side, we have two panes. One is a repository for the streams, the outputs, the models that we're going to generate. And then the bottom of it is CRISP-DM. Because CRISP-DM is very specific to SPSS and now IBM, they actually have a pane here that allows you to organize your project with respect to the documents and materials that you use to put together the business understanding, a folder for data understanding, a placeholder for data preparation. So you can actually type up screen capture things that went into data preparation and collect them in one single place. And then all the models that you built, the models that you finalized, you can put them in the model portion of the repository. Evaluation results can be stored, and deployment plans and procedures can also be stored. So it gives you a structured way to organize your project in such a way that when you come back to it a few months or years down the road, you would know what sources that you used, what outcomes that you generated, all in the same area, same location. So let's start building a small application. The way that you start is that you start with the sources, and then let's assume that our data is going to be a variable file. So these are the files that we have with the .txt extension or .cvs, comma separated values extension, or ASCII extension. So right click and say edit. It will bring up this dialog box where we're going to click on and see. I need to go back to my desktop, live lessons, data. In this case, let's grab a different data. Let's grab the data called diabetes. And it reads the data in, if you click on the next tab, File to Data tab, it automatically detects the field names and then the type of the fields. Notice that here we have 8 independent variables, the input variables, and 1 target variable, the output variable. The output variable is the class variable. It's a binary class variable. If you go to filter, if you want to exclude any of those variables, you can do so here. In this case, we did the pre-processing outside the tool, so we're not going to exclude any of those variables. Then we go to the types. This is a very important dialog box because this is where you validate the data types, and then you validate the roles that the data actually plays. Okay? So here, the categorical variable, the class variable, binary, is actually a flag. It's 1 or 2 or 0 or 1 or yes or no, and then it is the target variable. In rest everything else, we would like the tool to look at the data and figure out the variable range, variable type, whether or not there is missing values, okay, and finalize the validity of the data being usable. So we're going to say apply and OK. Next thing that we're going to do is we're going to go, see there are modules for record operations. These are the row manipulation, so you can actually sample, sort, balance the data set. There's field operations. Fields are the columns, the variables, so you can exclude or create derivative fields and variables into your data set. There is graphs that you can use to visualize different variables or variables collectively in a graphical output. And the modeling is what we're going to look at. We're looking at a classification. So on the left-hand side, as opposed to all, I'm going to click on classification. As you can see in the classification, we have some decision trees, some neural networks, some linear modeling, logistic regression. But what I want to do is I want to click on this automated. This is only available in IBM Spss Modeler. The good part of the automated modules is that it tests 2 or more different algorithms and model types, and then judges each and every one of them against each other to see which one actually predicts better for the given data set. As you will see, let's drag and drop our auto classifier because our problem is of classification type. We're classifying diabetes based on 8 different criteria. Okay? Then click on edit. There is nothing to read because the fields and their designations are being fed by the file reader node. Here, if you go to expert, C5 is a decision tree, logic regression. Let's take this out to be able to make the process faster. Let's not use Bayesian network, discriminant analysis. Let's keep neural network. Let's take out this decision tree, another decision tree, another decision tree. So we're going to have these 3, and we're going to maintain all 3 of them to see which one is better. And we want to keep all of the models, and we want to go back and say apply and say run. Total number of models be built is 3. As you can see, it completed and generated a trained model. If you go to the trained model, double click on it. So this is our C5 decision tree algorithm, an algorithm that's only available in IBM Spss Modeler. The next one is the neural network. So C5 actually produced better results than neural networks. And collectively, both C5 and neural network produce better results, better accuracies than logistic regression, which is a statistical technique. So here it shows different metrics by which the accuracy of the 3 algorithms, the model types, are judged against. The overall accuracy on a holdout sample, which we're going to talk about. If it doesn't make sense, it will in a few minutes when we cover the accuracy metrics in the next lesson. So overall accuracy-wise, C5 produced 83.98, so close to 84% accurate predictions of the whole data set, whereas the neural network was about 78.79%, and logistic regression was about 78% accurate. So what it does is that it runs quickly for multiple models, and if you wanted to create a model specifically, then you can go back here and drag and drop the model type like C5. Let's do that. I'm going to go back to modeling, all models, classification models, and I will take the C5. I will connect the data set to it. Okay, and then I'll execute it. As you can see, it was a pretty quick, and I want to be able to judge the accuracy. So I'm going to go to output. I'm going to take the analysis, basically analyzing the output, measuring the accuracy of it, connect it to analysis node. In the analysis node, I'm going to select coincidence matrix, also called the confusion matrix, also area under the curve as the metric, and I'm going to say run, and I'll look at the accuracy. See, 84% accurate on a holdout sample, in confusion matrix shows that testing the negatives are more accurate than testing accurately the positives because of probably the data imbalance problem. Area under the curve is about 89%, very, very good. So that, let me close this and double click on the model generated and go to viewer. It will show me the decision tree that it actually generated. If you go to the first note, you'll see that plasma glucose concentration was the most significant variable to differentiate between the ones that are diabetic from the ones that are not. Okay, so a numerical differentiation splits the data set into two, each of which further split until the leaf nodes are purified and concentrated to one class versus another. Again, we're going to revisit the decision trees and what they mean in a lesson that's coming up. So this is a short and sweet, if you will, introduction to one of the most popular industrial commercial tools that's called IBM SPSS Modeler. Now that we looked at IBM SPSS Modeler, one of the most popular commercially viable analytics environment, let's look at now to another environment, free open source, hugely popular, and its popularity is increasing as we speak. It's called R, and it's defined as a software environment for statistical computing and graphics. It is actually a part of free open source analytics tools environments that you can have direct access to actually carry out a variety of analytics projects. As you will see, it has very rich collection of functions and libraries for analytics and statistical computing purposes, as well as some graphical analysis. You can get R by simply going to r-project.org website. This is the website. After going through and understanding what R is, you can download R. For that, you need to find your mirror site based on your country. And US has quite a few of them. You can click on the very first one. Either one will work. And then you go to your download page. Then you need to pick your operating system. Is it Linux, Mac, Windows? As you can see, R is platform agnostic, meaning it works on Windows and Mac and Linux. Whatever your operating system is, click on that and then download the software. Once you download it, for instance, for Windows environment, it comes as a exe file. And then that exe file, when you execute it, will generate a toolbar icon called R. Depending upon what operating system you have, 64-bit, 32-bit, just fire it up. And this is the starting page for the most basic graphical user interface for R. Now, as opposed to teaching R, here we're going to look at a package within R, a graphical user interface package called Rattle that helps us use R functions without actually writing explicit R code. So for that, we're going to load the library, Rattle. Once we load it, all we have to do is call it, execute it, kind of shake the Rattle, if you will, and then click on it. This is the user interface that will help us carry out a variety of data mining and other data manipulation tasks using R libraries, R functions, without actually writing explicit R code. Now, as you can see here, there's a traditional pull-down menus, there is icon-based toolbar. It looks a little bit old-fashioned compared to some of the other tools that we looked at up to this point: graphically motivated, icon-driven, workflow enhanced. This does not have those, but it has a lot of good functionality that you can execute. So you can, the first thing is that you can get a data set pulled in. Data set could be of a spreadsheet type or a data that's generated with Weka, another free open source tool, ODBC, or data sets, you name it. Okay, here you click and say, I want to use, let's start with iris data set that we are quite familiar with. Say open, execute, and then it will show you that it has 5 variables, 4 numeric variables as inputs. And the very last one is a class variable, a categorical variable, which is the target. So this data set is designed for classification type analytics. So for the time being, let's turn partition off. Let's not split the data into subsets. Let's go to the next step, explore. Let's look at the summary statistics of the data set that we just pulled in. Click on execute, and it will tell you what kind of data types there is in the data set, how many observations that you have, 150 observations, 5 variables, 4 input, 1 output. The class variable has 3 unique labels, values, 3 different flower type. And then for each of those independent variables, you get all those numerical descriptive statistics, the minimum, the maximum, the mean, the median, and the quartiles. And it also gives you the class distribution on the output variable. So it's equally distributed amongst the 3 flower types. Then you can go to test tab and then conduct some statistical tests on the data set and different variables of the data sets like t-test, f-test, and Kolmogorov-Smirnov test, all of those, including correlation. We're not going to do any of those. Transformation, you can do imputation if there are missing values. You can do rescaling, normalization on the data. All of that are available to you. Then the very next one is the clustering, k-means and hierarchical. So there are 4 different clustering functions utilized in this particular graphical user interface that you can execute. They all use numeric data, so you need to find a way to convert your non-numeric data into numeric to be able to use most of these clustering functions. Then there is association rule analysis, market basket analysis, if you will, that requires a specific type of transactional data to actually generate the rules and the associations amongst those items, the events, the products that go together. The one that we're interested in is the model. It's the predictive model tab. So the first thing we're going to do is that we're going to build a decision tree. Run random forest decision tree. As you change your selection, the pane will tell you about which model it's using, which function it's calling, and how it does what it does. Let's start with the simplest one, a simple decision tree that will call R part, a function within our library, to build the tree for us. You can set parameters of this decision tree, minimum splits, minimum buckets, maximum depth. All of those are available to you to adjust. Now for timing, we're going to keep all the default settings and we're going to click on execute. And then it will generate the decision tree for us. And it will show it to us in a textual form, which is not very intuitive. So for that, why not go and click on draw? So it would generate us the graphical look and feel of the decision tree. Let's go back. And now let's go to evaluate. Let's select the error matrix, this confusion matrix, coincidence matrix is also called. We only have one data set, the whole data set. Usually is not a good practice, but we're going to come back to that. I'm going to click execute to see how good this model is performing. So this decision tree is about 96% accurate. It did 100% accuracy on the iris sentosa. It missed one of them on the iris versicolor, and 5 are missed and incorrectly classified on the iris virginica. Now what I'm going to do is I'm going to go back to my data tab and I'm going to grab a different data set. I'm going to click on and select diabetes data. Very simplistic diabetic diagnostic data set. And then, as you can see here, I have 9 variables, 8 input variables ranging from number of pregnancies, plasma glucose level, BMI, blood pressure, skin fold thickness. And then the very last one is the class variable, whether or not the person is diagnosed accurately as being diabetic or not. And for this, let's turn off the partition to look at the data, look at the summary statistics of the data set, all of the variables, variable types. There are two unique classes on the class variable, tested negative and tested positive. As you can see, it's not a perfectly balanced data set. 500 of the samples in the data set are from tested negative and only 268 of them are tested positive. So I'm going to go back here and then I'm going to split the data. To do predictive modeling properly, you need to do that. So I'm going to say 70% training and 30% testing, and I'm going to execute that change. I'm going to go back to my model and I'm going to say, build me a decision tree. And this is the decision tree. And then I can actually draw the decision tree. As you can see, it's a little more complex than the one that we built for iris dataset. In addition to decision tree, I also want to build a random forest model. I'm going to select forest. I'm going to say execute. This is my random forest model. And then I am also going to go ahead and produce a sport vector machine model. Okay, going to select that and execute it. And now that I have three models, I want to go ahead and see which ones are predicting better. And I go to my Evaluate tab. I select Error Matrix. And I want to look at the decision tree, the random forest, and sport vector machine. And then I want to click on Execute. Notice that it's only executing on the testing data set. So the 30% that it did not use is the one that the program is using to create the prediction results. So here we have decision trees. It's about 28% inaccurate on the test data set. These are the coincidence matrices. And for the random forest, it is now 25%, the error rate. And then for the sport vector machine, it's about 27%. So random forest was the best, followed by sport vector machine. And then the last is the decision tree. You can also go back to the model and say, I want the decision tree and tree only. And then I want to go to evaluate. I want to deselect everything, but want to keep the tree, and I want to see the area under the receiving operated curve, so ROC curve. And then when you click on execute, it will generate you this graphic. This gray line is the baseline, 0.5. This number closer to 1 means a better predictive model. And you want this red line to be as close to the upper left corner as possible. So it is predicting better than random chance, but it's not very, very good. Now, what I want to show you next is that everything that we did is get to be recorded on the log page. All those R codes, library calls, function executions, all those parameters, and then variable settings are recorded here. So if you look at how we did, what we did, in terms of the R syntax is concerned, you will find all that information in this tab. Basically, you can actually type the exact same comments with exact same parameters and generate exact same results without even using Rattle, this graphical user interface. So this is another way that you can get yourself familiar with different functions that R has for different predictive modeling modules and how to execute them and how to parameterize them so that it would generate the kind of results that you would like to get out of the tool. So let me show you one more thing. Let's go to cluster. And then let's use k-mean and say we want to generate 5 clusters. As you remember, number of clusters has to be set by the end user. There is not an optimal way for any tool or algorithm to optimally find the number of clusters. So you have to pick that and then say execute. It will generate all those clusters, all 5 clusters and cluster centers for you. And it will give you the numerical definitions of each variable as to how they define each of those 5 clusters. As you can see, it's very popular and very user-friendly interface to use Rattle to execute R code to do data mining without writing explicit R code. So this concludes my short introduction to Rattle and R in the context of predictive modeling and data mining.